And the group that's acting is a free group on two generators. And the only thing is I'm changing there's going to be, I don't know, 3 or 4 of these. I'm changing the what the generators do. So here, the base point, which I think is maybe over here, the generators are going to move by some kind of a large distance. I mean, I can figure out what the distance is, but that's not so important. And so here, the drift is going to be pretty large, so it gets to the boundary very quickly. Okay, now if you make the displacement smaller, you can make it smaller and smaller, it will somehow take longer and longer to converge to the boundary. The drift is going to be smaller. Okay, so the next one. By the way, this is the turtle program from Danny Caligari in hyperbolic plane. The only sort of disadvantage is that you have to put in the seed, and if you put the same seed in, you get the exact same random walk. It generates random numbers from the seed in some kind of a deterministic way. But anyway, so here you can see that I mean this kind of flies very quickly. Okay, so let's do now the next one, which I think is 4. 7. This is my favorite seed. Okay, so you can see that here it took a little bit longer. I mean, it took maybe a second to go to the boundary. And then the last one is actually very slow. I mean, you kind of start thinking that the theorem is not correct. But I don't know. I mean, this is maybe getting to...
You're just changing the
step, the translation distance, yeah. So it's always, the generators always, they move horizontally and vertically, but by less and less. And so this, and in fact it will look like it's not even converging, because it will sort of come back and so on. But it just, the drift is very small here. This kind of approximates the Brownian motion. You know, if you make the step very small, and you're sort of converging to the Brownian motion. And so it's not ready to converge. It'll in fact come back all the way to the origin. So it takes a while. Well, there we go. See, it's going back. The theorem must be false, right?
No.
Yeah, see, it's just... Yeah, the drift is very small here, so it somehow takes a while for it to...
So while it moves around there, let me ask a question. So if you measure the Hausdorff measure of the image of the sample path, is it ever bigger than 1?
Of the image of the sample, well, I mean, it's a countable set of points. I don't know how you could, I mean, you could connect them by edges, but it'll still be 1, right? Yeah, maybe is it done? Yeah. Anyway, I don't know if it's, maybe it's done. Yeah, it doesn't seem like it's moving anymore. Okay, but anyway, you see the what the spirit here is, that if the steps are small, then the drift is going to be small. And okay, I guess we can. Stationary measures are, and remind you about the Hora function boundary. And then we can start proving this. Maybe probably not today, but next time. Okay, so let's start with generalities and measures. Okay. Okay, so first of all, if I have two probability measures on, I guess that's a bit of notation, P of G. So this is the set of probability measures on G. Then I can form the convolution. Okay, that's maybe the main operation that you have here if you have measures on groups. So this is the convolution. And what is it? So it's also a probability measure on G. And what is the measure on some group element G? Well, it's the sum overall H in G of, take mu1 of H, and then you multiply by mu2 of H inverse G. Okay, so what's the idea here? Well, you want to know, you're going to take a random first step according to the measure mu1, and then you're going to take a random step according to measure 2, and you want to know what the probability is of getting to G. Right? So this intermediate, so for the first step is H. So this is sum, you have to sum over all possible first steps. Okay, and this is of course the same as the sum over H1, H2 equals G of mu1 of H1 times mu2 of H2. Okay. Okay, now more generally, suppose you have suppose your group is acting on some space M. M is some topological space, and the action is by homeomorphisms. Okay, and if I have a measure mu that's on G, probability measure on G, and I have another measure that's a probability measure on M, right? So I have some. So M, maybe this good example is the boundary of X, and then you have some kind of a stationary measure there. Okay, then you can define, in the same spirit, you can define the convolution of mu and nu, and this is going to be a measure on M. And how is it defined? Well, mu star nu. Okay, let's do it like this. This is the sum over all H in G of, you take mu of H, and then you take H star of nu. So this is the push forward. This is, H is a homeomorphism of M, and I can push forward the measure by this homeomorphism. And that's, in the case when M is equal to G, you get the same formula. The push forward by H is really H inverse G, right? Okay, so these are kind of natural things you can do. And then what is a stationary measure, or mu stationary measure? Okay, so definition. So nu in P of M is mu stationary if mu star nu is equal to nu. So you convolve with your measure mu, and you get the same measure. It's invariant under convolving like this. So maybe when you unwind this, so this just says that measure of some set U, this is going to be the sum over all group elements. So mu of G, and then you have mu of G inverse of U. Okay, that's somehow when you unwind the definition of convolution, this is what you get. And this is somehow what hitting measures should satisfy, right? Why is that? So here's my space, here's the boundary of x, and I have my base point over here. And I'm wondering, and then I have some set u in the boundary, say, okay? So I want to claim that the hitting measure is if we don't have it yet, but if you had a hitting measure, then it would have to satisfy this. Okay, so what is the probability that your random walk will end up in U? Well, it's so that's what the left-hand side is supposed to be. Well, we break it up according to the first step, right? So there are infinitely many possible first steps, that bring you to some kind of a g here. So here's g of x naught. Maybe this is the first step. The probability that you will take that first step is this. And then once you're here, what is the probability that the random walk that starts here will end up in U? Well, everything is equivariant. So going from here to U is the same as going from the original point to G inverse of U. You can just apply G inverse to this situation. Right? The probability of going from here to here, this probability is the same as the probability of going from x0 to whatever the G inverse of U is. These two have the same probability because they're off by, the group is acting by isometries here. So going from here to here is the same as going from here to here. And that's what this is. Okay, so any hitting measure should satisfy this this equation. Okay. Okay, and as I said, the first step is going to be to construct a new stationary measure in the Gromov boundary. That's already called step 1. There exists a mu stationary measure on the boundary of x. Okay, so we'll have to work to prove this. Okay, so maybe what makes sense is to give you the proof in the compact case. And then talk about the Hora function boundary a little bit. Okay, so let's do that. Okay, so that's a lemma, and it's a very classical lemma. Yes. That if G is acting on M, and M is compact neutralizable. Okay, then and mu is our probability measure on G, the one that defines the random walk. Then there exists a mu stationary measure mu. Okay, so as long as the space is compact, then you're fine. And our problem is going to be that the space of interest is not compact. Okay, so there are two proofs. One is really easy using this Schauder's fixed point theorem, but it'll turn out that we'll need this a little bit of extra information given by the first proof. Okay, so what do? We say, so mu n tilde, this is going to be the push forward of mu, you convolve mu n times. So what is this? This is the probability measure associated to taking n steps in the random walk. Right? So the value at G is that, that's the probability that your random walk after n steps will be at G. So we take the push forward of this by the orbit map. Under the orbit map from G to x. Okay, so we have you imagine here's x, and then you have these points. The orbit is some kind of a countable set, and we're pushing forward this G. So we get some kind of a measure on x. It's a probability measure on x, and we'd like to take limits. Well, it's M. In the lemma, it's M. So we'd like to take limits. Okay, now one problem is that the limit may not exist. I mean, we just don't know. Now, in analysis, there is a standard trick that if you have a sequence that doesn't converge, then you make another sequence that has a better chance of converging, and that's the Cesaro averages. So you take, you replace the nth element of the sequence by the average of the first n elements. So like 0, 1, 0, 1, 0, 1, that doesn't converge, but when you average, it'll converge to a half. Okay, so this is exactly what we do. So we take, so let mu n bar, this is going to be mu1 tilde plus mu n tilde over n. So this is just a Cesar average of these. Okay, now this space P of m is compact. Okay, so I don't know to what extent I should, this gets some, there's always, annoying thing to think about functional analysis. But the space of probability measures is, on the compact space, is compact. So a fancy way to say it is that, this space of measures is the dual of the space of continuous functions. So I can look at the space of continuous functions on M, and that's a certain Banach space with, sup norm, and then you can take its dual. And the dual, this is called the Riesz representation theorem, and I'm sure, I think in the US that's one of these things you have to, when you take an exam, first year course exam, then you have to know Riesz representation theorem. Okay, so this is one place where it's actually useful. So C of M, this is the Banach space. You take the dual, and that's the space of measures, signed measures, I guess. Signed measures on M. And inside it you have this P of M. And this P of M is contained in a ball, in a unit ball in this space. Okay? And the topology on this space comes from C of M. In other words, a sequence here converges if for every continuous function when you integrate the function. So the pairing here is integration. When you integrate maybe I'll just say it like this. So the sequence of measures, so mu I, when do these measures converge to mu? Well, this if and only if for every function, for every continuous function on M, the integral of f d mu I converges to the integral of f d mu. So that's the topology comes from the pre-dual. And then it's a theorem in analysis that with weak star topology, closed balls are compact. So this P of M is going to be compact. But you can also prove it bare hands. I mean, you can take, so there, the set of functions, let's say bounded by 1 or something, is separable. You take a countable dense collection, and for each function you can choose a subsequence. Given the sequence of measures, you can choose a subsequence so that the sequence of numbers converges to something. And you do it for a countable dense set, and you choose there's a diagonal sequence, and anyway, there's a proof like that, and you can do that. It's completely elementary. But if you want to be fancy, then you say Riesz representation. You say it's weak star topology, and so on. Okay. All right. So where are we? Yeah. So we have these measures. And by compactness, we know there is some subsequence that converges. Okay, so mu n bars will converge after a subsequence. So let mu be a weak star limit point of these mu n bars in P of M. Okay, so some subsequence will converge in that sense to some measure that we'll call mu. And now the claim is that this is in fact stationary. Mu is mu stationary. Okay, so why is that? Well, so we'd like to convolve mu and nu. So we look at these approximating things, so mu n bar, and we convolve mu n bar. So what is that? Well, when you convolve one of these tildes, right, you get the next tilde. Right? If you convolve mu n tilde, you'll get mu n plus 1 tilde, right? Because these are n-fold convolutions. So this will be mu 2 tilde plus mu n plus 1 tilde over n, right? The indices will shift by 1. And so what's the difference? So if I take this convolution and I subtract mu n bar, then everything will cancel except for the mu 1 term and mu n plus 1 term. But also between 0 and 1. So this is something less than or equal to 2 over n. And so that means in the limit, these will be equal. So this implies that mu is there. And that means nu is stationary. Okay, that's one proof. And the more sort of high-powered proof is so this is really, I guess this is called Schauder-Tikhonov fixed point theorem. So this says that if you take so if K in V is a compact convex subset of a locally convex topological vector space V, then every self map from K to K has a fixed point. Okay, so the original theorem by Schauder was for norm spaces. V was a norm space. Unfortunately, our space of interest, this P of M, is not a norm space. There is a norm, but it doesn't give you the right topology. The right topology is the weak star topology. So then Tikhonov generalized it to spaces that don't have a norm. In fact, this is what's called a Frechet space. It's given by countably many norms. Anyway, so we can apply this to so V is going to be our the dual of C of M, the space of signed measures, and K is P of M. That's convex, right? You can make convex combinations of measures, and that'll be, or probability measures. That'll be a probability measure, and then the function is the function sends nu to mu star nu. That's a function from K to K, and you check that it's continuous, and it's so it has a fixed point, and that's a stationary measure. Okay. Okay, so basically we are done done with step 1 if boundary X is compact. That's what this says, right? But now this is where we have to work harder, when boundary X is not compact. Okay, so this is where I want to remind you about a Hora function boundary. Okay, so there's a basic phenomenon in hyperbolic spaces that are not locally compact. Given a sequence, what can happen to a sequence in a hyperbolic space? So let's just start with that. So basic phenomenon. So every sequence xn in X hyperbolic, delta hyperbolic, has a subsequence so that one of the following, so that either, okay, so the first thing is that the subsequence, let's call it xnk or something. So this subsequence converges to some point in the boundary of x. Okay, so that's good. So in the locally compact situation, if x is like a hyperbolic plane, this will always happen unless the sequence is bounded. And if it's bounded, then you can take a subsequence so it converges to a point in the hyperbolic plane. In general, when x is not locally compact, then this convergence in the hyperbolic plane or whatever has to be replaced by something weaker. And the weaker thing is, this is called coarsely rotates. So x and k coarsely rotates about some x in x. Okay, so what do I mean by this? Maybe before I define it, let me give you an example. So let's say x is a wedge of infinitely many rays, like this. So this is it's a wedge from 1 to infinity of I don't know, 0 infinity. It's like this, where I'm wedging it at 0. Okay, and then I take so this is not locally finite, and I take a sequence where it'll go to infinity. The first point x1 is going to be on the first ray at some distance 1 maybe. x2 will be on the second ray, distance 2 from the origin, and then x3 will be at distance 3 on the third ray, and so on. Well, that sequence does not, it's unbounded, but it does not converge to any point in the Gromov boundary, because the Gromov boundary is just a countable set. So boundary of x is just 1, 2, like that, 1 point for every ray. And this sequence doesn't converge to any one of them. What happens instead is that the sequence rotates around the origin, in the sense that if I take 2 of these points and I join them by a geodesic, the geodesic will pass through the origin. Okay, so this coarsely rotates is just a coarsening. I mean, this is in a tree, but in general, you'll have to put in some deltas instead of saying that the geodesic between 2 points passes through 0. It will just be passing through some neighborhood of 0. So okay, so what does that mean? That it coarsely rotates about some x. It means that so any geodesic from x and k to x and l for k not equal to l. So you take 2 distinct points in your subsequence and you join them by a geodesic. This intersects the ball centered at x of radius. Now I'm going to be generous, I'll say 20 delta, but the real number is probably more like 3 delta or something, or 2 delta. But it doesn't really matter, some fixed number of deltas. So the picture is kind of like this, except that it's coarse. So here's x and here is this ball, and I have this sequence of points, and no matter what I do, which 2 points I pick, the geodesics between them will always intersect this ball. Okay, so somehow you can think of these points as just rotating around x. They're going in different directions out of x. Okay, so that's a phenomenon, and maybe I'll just say a few words about how to see that. So basically, it's like this. You give yourself some base point, maybe p, and then you consider these spheres of radius, maybe 5 delta, and then there's 10 delta, like that, and then 15 delta, and so on. So in increments of about 5 delta, you look at these spheres, and you have your sequence, and you can ask yourself if there is a subsequence of your sequence that is outside a particular ball, right? Let's say this ball here. Is there a subsequence of that sequence outside this ball, so that when you project, nearest point project, so you have a point over here, you can draw a geodesic to P, so your nearest point project to the sphere here. And the question is whether I can do this. I can choose a subsequence so that these nearest point projections are all within 2 delta of each other, say. Okay, so for any given, k times 5 delta, ask if there is a subsequence outside this ball of radius k times 5 delta that projects within 2 delta of each other, within the delta of each other to the sphere. Okay? So you can ask this for any particular k. And so the procedure is I look at the first sphere and I pass to a subsequence. If I can, I pass to a subsequence that works for that sphere. So it's some subsequence outside this ball, and the projections are all within 2 delta. Then I take that subsequence. So in the end, I'll have a diagonal argument. So I just look at that subsequence and I ask this question for that subsequence. So can I pass to a further subsequence so that lives outside the second ball, and so that the projections are all within 2 delta of each other? And I keep going like this. If I succeed at every step, for every sphere, I can find a further subsequence so that I get that. Then the diagonal subsequence will actually converge to a point in the Gromov boundary. Right? So if you succeed, so inductively, for k goes 1, 2, 3, and so on, keep passing to subsequences as above. And then, so if success, right, then the diagonal subsequence converges in the boundary of x, because the diagonal subsequence will be it'll be a quasi-geodesic. Eventually you'll be projecting to a particular 2 delta neighborhood of some point on every sphere. And so they'll give you a point in the Gromov boundary. And the alternative is that for some k this fails. So you keep going and you get to k equals 100 and it still works, but for k equals 101 it doesn't. Well, what that means is that you're rotating around that common projection on the previous step. Right? If all the points project to a point like this, but there is no common projection on this sphere, then these geodesics will all kind of look like, they will all kind of, they'll have to pass near this point, but they will not be passing within, they will not be, they will be kind of spread out in different directions on the next sphere. When you pass to a suitable subsequence, the projections here will all be far apart on the sphere. Okay, so this is maybe something to think about, but that's the level of the argument. You can make the argument like this. Okay, and so you can see that in the compact case, when each sphere is compact, then just by the pigeonhole principle, you can always arrange this. But when the space is not locally compact, then this contains infinitely many points there. You can find arbitrarily many points, or infinitely many points that are all more than 2 delta. In the case of this tree, right? You can find infinitely many points. They're all uniformly far apart from each other on this sphere. Okay, so that's somehow the something to keep in mind.
Is that unbounded sequence, right? For xn must be unbounded. There is.
Well, if it's bounded, then it coarsely rotates. If it like a constant sequence coarsely rotates, constant sequence coarsely rotates around itself.
Oh, I see. Okay.
That's right. Yeah. So once, I mean, it could be that the sequence is not bounded; it somehow stays inside one of these regions here. But then it'll coarsely rotate, about this point as well. That's why I want 20 delta, just to give me some room. But that's important. Okay. Okay. So what does the Horo function compactification do? Well, it sort of neatly keeps track of this phenomenon. Okay, so the Horo function construction, Horo function compactification. Okay, so I have this x, And what I want to do is embed it in the space of functions. Okay, so this x will get embedded in the space of Lipschitz functions. These are going to be one Lipschitz functions with the base point p of x. Okay, so p is in x is some base point, and I'm looking at the functions f from x to r. They're one Lipschitz. Okay, so they don't they decrease distances. They're one Lipschitz, and they're normalized so that p goes to 0. Okay. And somehow the main thing here is that you can. So what is this embedding? So given a point x, you send it to the function bx. Okay, so b really stands for Boseman, I guess. This is Boseman's construction, although he didn't really think of x as being locally bad. You know, he was thinking about manifolds mostly. Okay, and this function bx sends so bx of a point y. Well, this is going to be basically the distance between x and y, but it needs to be normalized, right? So we want this function to take value 0 at p. And so I have to subtract the distance between x and p. Okay, now, so how should you think about this? Well, let's say you're in the plane. Let's say x is the plane. Of course, our interest is in hyperbolic things, but let's say it's a Euclidean plane. Then p is the origin, and I take some other random point here. What you should be thinking about is level sets of this function. So this is really the distance function from x. So I'm looking at circles. Those are the level sets of the distance function. And one of these circles will pass through p. And then this is normalized so that the level through p, this is really 0. And it's negative when you go towards x. So this point here represents the function, it's a level set with some negative value, negative distance between x and p. But these are the level sets. But now what happens when x goes to infinity? When x goes to infinity, these level sets, these circles, will become more and more like lines. And so in the limit, when x goes to infinity, to some point in the, let's say, S1 infinity, there's a natural circle at infinity. When x converges to some point xc, say, in that circle infinity, then what you're going to get, these level sets will converge to some, to a collection of, the level sets are going to be parallel lines. And there's going to be one through the origin, and that one will have, label 0. It will correspond to a preimage of 0. And as you go towards xc over here, the function will be negative, right? It will be negative this way and positive this way. Okay, so that's somehow what's going on here. You're normalizing these level. You're looking at the level sets and passing to the limit the level sets. And so the key claim here is that this is compact. So if I take the closure xh bar, so this closure in the space of functions is compact. Okay, so why is it compact? Well, that's if you want, Arzelà-Ascoli. It's the Arzelà-Ascoli theorem. So all these theorems that you learn in first year as graduate students, they're all very useful here. Okay, so this is called the Horo function compactification. So xh bar is the Horo function compactification. Okay, so what happens here in this example? What is the Horo function?
Did you define the x at h?
That's the closure. That is the closure of x. Closure of x in the space. Yeah. So, for example, in the case of the plane, this function here, the one you get by taking limits, that belongs to the Horo function compactification. Okay, so what happens to this example here? What is xh bar here? Does anybody know? In particular, if I take a sequence, so I'm going to have a point in xh bar that corresponds to every ray. There's going to be I can take a sequence of points x along the ray, and then in the limit, I'll get the Horo function that corresponds to an endpoint. Right? What is, for example, what is the Horo function that corresponds to this first endpoint of ray? So here's my C1, for example. Let's see what the C3 and so on. What is this function? So b sub C1, for example. This is the limit of b sub xn, where xn is here's x1, x2. Okay, so what do I know about this function? So it will be 0 at the origin, just because all these functions are 0 at the origin. And if I move towards the point, it decreases, right? So it will be -1 here, -2 here, -3 here, and so on. Okay, what is it going to be on the next ray? It'll be 1, 2, 3, and so on, and 1, 2, 3, and so on. Right? Basically measures the distance from your base point, bxn. You have to measure the distance to bxn, and then you take the limit, and this is what you get. Okay. Now, what is the limit of? So now I have, and similarly I have functions for the other x's. So then I want to ask you, what is the limit of bx sub n? What is that function?
It's really decreased, push 1, really increase for other rays.
But what about the limit? So big C1 decreases along the first ray and increases on all the others. Big C2 decreases along the second ray and increases along the others, and so on. But now I'm taking the limit. So big C infinity, if you want. What does this function do?
Increase all
Increases on all of them. And what is that function called otherwise? It's bx0, exactly. It's b0. So what happens is that these points in the Gromov boundary, they converge to this point. So the compactification, really, you should draw it like this. These rays are getting shorter and shorter. And the sequence of points converges to the wedge point. This is the compactification. This is really the main example to keep in mind. Okay. Yeah, let me just say one more thing and then we'll stop and complete step 1 next time. For the, okay, so facts to check. I don't know. In a similar way as computing that example, you can do. Okay, so let's suppose you have a sequence. So bxn converges to b in x. Well, like this. So you have a sequence of Horo functions associated to. So xn is a sequence in xn. I start with a sequence in xn and I look at their functions, and they converge to some function b. Okay, so if xn converges to c in the Gromov boundary, so this is the first possibility in my in that basic phenomenon business, right? So I have a sequence that converges to a point in the Gromov boundary. Then what can I say about this function b? Okay, so I have a sequence of points in the hyperbolic space converging to a point in the Gromov boundary, and the corresponding functions, Horo functions, converge to a Horo function. Then what do I know about the Horo function? Okay, well then this b converges to -infinity along any quasi or I don't know geodesic ray in X that converges to Xi. That goes to Xi. Okay, so this is what we did in the case of a tree, right? So I have the sequence of these xn's, and they converge to Xi, and I have the associated Fourier function. Well, if I take any ray that goes to Xi, then along this ray, my function b will be going to minus infinity. That's what happened with Xi1. That's what you computed here with Xi1. But it's true in any hyperbolic space, right? So we have a sequence of points going to this Xi1, then along this ray, the function goes to minus infinity. Okay, so I won't do the details of this, but it's very, it's an exercise. And b goes to, where does b go if I take a ray that doesn't go to Xi, goes to some other point? Just thinking about that example. If I take a ray that goes to some other point, then b goes where? Well, where does it go here? Plus infinity, right? It goes to plus infinity along any ray that goes to Xi prime not equal to Xi in the Gromov boundary. Is that okay? Should I do one of these? Maybe I'll do the next one. It's all very similar. You just have to do some. You can always pretend you're in a tree, right? The hyperbolic space is like a tree, except for a few deltas. Okay, so the second claim is that if xn coarsely rotates around x, then B has its coarse minimum where it doesn't go to minus infinity anywhere. It has its minimum while coarsely minimum where? Okay, so I shouldn't have erased it, but where was the minimum of that function? It was at 0, right? Is its coarse minimum at x. And this coarse minimum is roughly equal to minus the distance between p and x. In our case, that was 0. But if it rotates around some other point that's not the base point, then this minimum would be negative the distance, up to a few deltas. Well, I don't know. Let's just do one of these and just put the kicks, right? There's p, here's Xi at infinity, and I have this ray that goes to Xi, and then I have the sequence xn that converges to Xi. So what does that mean? Well, it means that this xn, if I was in a tree, then the picture would be like this, right? The nearest point projection to this ray would be getting closer and closer to Xi. And in a hyperbolic space, it's not like this. It's more like some kind of a thin triangle picture. But this is right. So this is xn. This is xn plus 1, and so on. Right. This is what it means for xn to converge to Xi. You look at these nearest point projections to the ray, and they're getting closer and closer to Xi. Okay. Now, what is b? So I'm thinking about proving this first claim, and the others are proved in exactly the same way. Okay, so I want to show that b goes to minus infinity. Well, I want to consider some point q. So I want to see that if this distance is large, I want to see that the limit b of q is a very negative number. Okay, well b of q is approximated by b sub xn of q. But what is b sub xn of q? Well, by definition, this is the distance between q and xn minus the distance between xn and p. That was the definition of this function b sub xn. Well, if we were in a tree, so distance from q to xn is this, and distance from xn to p is this. So when I subtract, I'll get the negative distance from P to Q. And of course, you're not in a tree, you're in a hyperbolic space, so this is off by a few deltas. Okay, and this is now independent of n, so when n is large, this is going to be the answer. Okay, so it goes to negative infinity, and the value at Q is negative distance from P, just like in our example. And you by a similar kind of a calculation, you can prove all these other claims. Okay, so let me just summarize, and then we'll stop. So we have a function from, okay, so this will be called phi, I guess, and it goes from this Hor function boundary into x union boundary x. We want to relate the Hor function compactification with the Gromov boundary. And this xh bar, this breaks up into two pieces. It breaks up into xh bar infinity and then xh bar finite. So this infinity is where the infimum is negative infinity. So you take the set of functions b whose infimum is negative infinity. So that corresponds to sequences going to a point in the boundary. These functions go to negative infinity. If you have rotation, then infimum is finite, and it's equal to this. Okay, and here the infimum is greater than negative infinity. So you just break up the space into these two kinds of points. And phi is going to send this the infinity part. The infinity part will go to the boundary of x. And the definition is just, it's going to be a unique point where the function is negative infinity. So there's unique, so phi of phi, so on h xh infinity, phi is the unique xi in the boundary of x, where so that this function b of xi is negative infinity. Yeah, that's what this A is saying, that in this situation here, there is a unique point in the boundary where the function is minus infinity, and all the other points in the boundary is plus infinity. Okay, so this phi is just going to pick out the one where it's minus infinity. And then on this finite part, it's the local minimum. So phi is the local minimum, the global minimum, the minimum, coarse minimum, I don't know. And it's only coarsely defined on this set. So here, this part goes to x, and this part is only coarse. This is a coarse map. You don't have the exact minimum, but you only have it up to some bounded set. Okay, so our strategy is going to be to make a stationary measure on this space, which is compact, so we already know how to do it. That's the lemma. And then we'll want to argue that stationary measure is supported on the interesting part, on the infinite part, not on here. The measure is 0 here. Any stationary measure is going to have measure 0 here. And then once we know it's supported here, then we can push it forward to the boundary, and that's going to be the construction. Okay, so we'll see that next time. And I guess it's 4:30, so this is a good time to stop.